Hello everyone, my name is Shu. I'm presenting our work, OpenGAN, Open Set Recognition via Open Data Generation. This work is supported by CMU Argo AI Center for Autonomous Driving Research. We motivate our work by the safety issues in self-driving, where we have many machine learning models. Usually, we train the models in a closed world paradigm. For example, we train a K-way classification model on a dataset that has K classes, but the model will not perform robustly in the real open world, where we have many unknown objects outside the K classes. It is crucial to recognize them for driving safety. Otherwise, for example, a Tesla Model 3 vehicle failed to recognize the unknown overturned truck, and it just crashed into the truck. Detecting the unknowns is crisply formulated as the open set recognition through the lens of image classification. Specifically, we train models to predict the class label if the input image is from the K closed set classes. Otherwise, flag it as an unknown example. We address open set recognition in this work. Let me show off our contributions. First, we propose a very simple method called OpenGAN. It learns a lightweight network for open set recognition on top of the K-way classification network. Second, our OpenGAN achieves the state-of-the-art performance under different setups. Third, we introduce a more realistic protocol to study open set recognition through semantic segmentation. This makes open set research more applicable to real-world applications. The current setup for open set recognition is to split a dataset like MNIST into closed and open sets. The closed set can be digits 0 through 5, and the open set are digits 6 through 9. We train a K-way classification network on the closed set only, but test the network on both closed and open sets. Usually, we compute uncertainty score at the open set likelihood for open set recognition. One simple approach is to use the inverse maximum of softmax probability produced by the K-way classifier. Now let's consider an atypical setup where we have outlier data during training. Can we use outliers to train our model to address the open set? The answer is yes. In fact, a previous method called outlier exposure trains a very simple closed versus open classifier to recognize the open set. This method works quite well on some benchmarks, but it fails once the training outliers do not represent the testing open set. Please note that using outliers during training is realistic because the outliers could be from out-of-domain data for free. Now let's consider the case when we have little or no training outliers. Is it possible to generate fake outliers like using a GAN? The answer is yes. There are many methods that use GANs to generate a fake open set data during training. One idea which was not sufficiently explored in the literature is to use the GAN discriminator as the open set likelihood function for open set recognition. Because the GAN discriminator is learned to recognize the data distribution of the closed set. We tested this idea, but this doesn't work. This is because of unstable training of GANs. Please also recall that by design, learning a GAN should end up with a discriminator that is unable to distinguish synthetic open set data and real closed set images. Our proposed solution is OpenGAN, which trains a discriminator with both real outliers and synthetic data generated by a GAN. Intuitively, it combines outlier exposure and GAN, but combining the two makes a huge difference. On the one hand, like a GAN, it generates data to better span the open world. On the other, like outlier exposure, it uses training outliers to stabilize the training of GANs and to select the right discriminator for open set recognition. In short, the discriminator here is for both open set recognition and GAN training. Our final version of OpenGAN runs on the off-the-shelf features rather than pixels. The features are extracted from the K-way classification network. We find it more efficient to generate features than pixels. When using features, we can train a simple multilinear perceptron as the GAN. Moreover, OpenGAN strives to learn a robust discriminator rather than a generator. In contrast, Existing GAN methods commonly focus on learning a good generator to generate realistic images. Lastly, OpenGAN uses the GAN discriminator as the open set likelihood function. In contrast, other GAN methods usually use the reconstruction error as the open set likelihood. Apparently, these methods will not work well on high-resolution images which are hard to reconstruct. We validated our OpenGAN under 3 setups and used 2 metrics, AUROC and the F1 score. We compared against the various methods. Please refer to our paper for details. The first setup is the typical one which we explained earlier. We follow the literature and use some popular datasets. It is important to note that in this setup, we don't have a training outliers. Our OpenGAN becomes a typical GAN, but we use the validation set to select the GAN discriminator. We call this version OpenGAN 0. Here are the results. First, OpenGAN 0 clearly outperforms all the other methods. Second, when building models on features rather than pixels, we achieve better performance, for example, nearest neighbors and OpenGAN. The second setup follows a less biased protocol which uses cross-dataset images at the train, validation, and test sets. For example, we use the tiny ImageNet as the closed set for 200-way classification. We use SVHN as outlier data for training and validation. As for testing, we use a third dataset and NIST as the open testing set. Because we have multiple datasets, we use one dataset at a time as the training outliers and the rest as the testing open set. We did all the combinations and reported the average performance for each method. I summarized 3 salient conclusions. First, methods like OpenGAN perform much better on features than pixels. Second, training with outliers, the simple closed versus open classifier, or CLS, already outperforms prior methods. Third, when we treat the outlier data at the k+1 other class, we train a k+1 way classification network and use the k+1 softmax score at the open set likelihood. This works quite well. This is the TSME visualization on the off-the-shelf features computed by the K-way network for tiny ImageNet classification. We can see the closed set tiny ImageNet and the open set images from other datasets are well separated. Recall that the TSME is a nonlinear method for visualization, and our OpenGAN learns a nonlinear MLP at the discriminator. This intuitively explains why OpenGAN works. The third setup is our proposed one that studies open set recognition through semantic segmentation. In other words, this is open set recognition at a pixel level. In other words, we use the well-known cityscapes dataset, which ignores a large amount of pixels, which we call other. In the ground truth semantic segmentation maps, we can see other pixels contain diverse objects, such as strollers and a street market. It is worth noting that state-of-the-art segmentation networks, such as HRNet, were not trained on these other pixels. As a result, the HRNet misclassifies the unknown stroller as a motorcycle and the street market as a building. This will cause catastrophic issues because those objects require different motion plans for driving safety. We split the cityscapes into our training, validation, and test sets, and use AUROC to measure the performance for open set pixel recognition. Here are 3 salient conclusions. First, when we train a k+1 way HRNet, it works quite well for open set pixel recognition. Actually, this model keeps the accuracy on the k classes, just like the standard k-way HRNet. Therefore, we suggest that our community not ignore the other pixels, but instead taking all of them to improve models' robustness. In fact, classifying all pixels was a common practice many years ago in the Pascal VOC dataset. Again, our OpenGAN feature performs the best. This is because of a more balanced sampling between closed and open set pixels when training the OpenGAN. Because we use the HRNet features to train OpenGAN, we maintain the state-of-the-art semantic segmentation performance on the k classes. It is worth noting that the street market is a true open set object because there's not another similar street market that is as big or selling clothes in the cityscape training set. Now let's visualize the synthesized RGB images by OpenGAN. For OpenGAN pics, we train it to synthesize patches. We also try to train it to synthesize the whole cityscape's images, which are 1K by 2K, but it doesn't work because of the difficulty in synthesizing high-resolution images. As for OpenGAN feature, it is non-trivial to synthesize RGB pixels because it operates on features. To synthesize RGB patches, we do it analytically. For each synthesized feature, we find its nearest neighbor per pixel feature in the training set and use the corresponding patch as the synthesized patch for OpenGAN feature. We can see that OpenGAN feature can synthesize unknown objects, such as the back of traffic signs and roadblocks, which are not from the K-closed set classes. In contrast, OpenGAN pixel only synthesizes realistic RGB patches in terms of color and tone. This intuitively explains why OpenGAN feature performs much better than OpenGAN pixel. To end the talk, I'd like to emphasize 3 points. First, to make sense of open set recognition research for real-world applications, we should go beyond the toyish MNIST dataset. Second, we should embrace outlier data during training to improve the open world robustness and safety. Third, without outliers, let's synthesize them. Thank you.